Nuclear binding energy. A nucleus holds Z number protons and N number neutrons. The total number A equals Z plus N is termed the mass number. Nuclides of the same A value and different Z and N values are isobars. The nuclear constituents are held together by nuclear forces. The nuclear binding energy is the energy required to disassemble a nucleus into separate protons and neutrons. For a given mass number A, the binding energy is largest at some balanced Z and N values. Display 2 depicts isobars with excess protons as beta plus emitters. They reach the lowest energy state and, thus, the highest binding energy per nucleon. Isobars with excess neutrons are beta minus emitters. They reach the lowest energy state and, thus, the highest binding energy per nucleon. Display 1 depicts a sample of isobar nuclei. On the left side of the table are isobars with an excess number of neutrons. They are beta minus emitters. On the right side of the table are isobars with an excess number of protons. They are beta plus emitters. In the middle of the table are the nuclides of the largest binding energy in an isobars row. Display 3 depicts in gray a plot of experimental largest binding energy per nucleon among the isobaric nuclei, viewed in display 1, versus the mass number A. The smooth red curve represents the liquid drop model binding energy per nucleon. The data is magnified by a factor 50 at the selected point. It shows that the even nuclides, that is, of even numbers of both Z and N, always have the largest binding energy per nucleon compared with adjacent nuclides. Display 4 shows that the atomic number Z of the selected nuclei in display 3 varies rather linearly with the mass number A. Visit the website www.cyberphysics.academy for a full view of the tutorial. Send comments to contact@cyberphysics.academy.